Alright, so here we are back again. I'm doing a little bit different video format, so it might be a little shakier on this one. We'll see how it goes, and we'll go from there. So basically what I'm doing is, once again, what do we need to do? And so we have a pocket full of things. Ohm's law, voltage divider, current divider. We have KVL, KCL. We have node. We have mesh. We have superposition. We have source transformation. I'm not going to write it out. I don't think I'm going to write superposition out anymore. And we have Thevenin. And we also have Norton, but we're not going to do too much with Norton. We're just going to do Thevenin for the most part. And everything that works in Thevenin works for DC. Everything that works in that box works for DC. It works for frequency domain, time domain, it works for AC frequency domain, and it also works for AC frequency domain. AC, and this is RMS frequency domain. Okay, this is non-RMS, and this side over here on the right is RMS, which is what we want to use and make it easy. I mean, if you want to make it hard for you, do non-RMS, and then you have to convert to RMS. And the big difference between AC and DC, or time domain and frequency domain, is P and Q, power, and P and Q, power. So we're going to stick with AC RMS values because it's just easier to start with, end with, and stop with. So just to give another overview of what's going on, everything works. Again, you had DC voltage and it was on or off. IDC was on or off. On or off. Okay, you had a V/T value, which was an AC value that was, Vmax cosine omega t plus or minus theta V. And you had an I of t value, which equaled Imax cosine omega t plus or minus theta I. And then you could turn those values. You didn't have to worry about this per se, the IDC and the VDC in either one of those domains of the RMS or the frequency domain, either frequency domain, non-RMS or RMS. But in the RMS, you basically had a phasor, which was V, equaled Vmax divided by the square root of 2 at an angle of theta V, whatever that was. And you had Imax, or I, phasor, IRMS. I should probably put RMS here, RMS, just for the heck of it. This was Imax divided by square root of 2 angle theta I. Okay, so that's RMS domain. So you had to go in and you had to take this Vmax to get it, and Imax, you had to divide it by the square root of 2. So if we just say that it's VRMS to begin with, we don't have to divide by the square root of 2. Just saying. So if we assume those values of V and I are already RMS, then we don't have to divide by square root of 2, and we're good to go. That's the easy way to do it. If you're just going to stay in the non-RMS frequency domain, then V non-RMS is just Vmax angle theta V, and I non-RMS is just Imax theta I. We'll get into this a little bit deeper here in a little bit, but first I just want to kind of go over AC frequency domain, RMS frequency domain. And for the time domain, C was in farads, L was in henries, HENRY. Maybe I should see if I can erase this. Nope, can't do that. HENRY, Henry, and resistors were in ohms. Okay, and then we had to switch everything. We had to have an XC value, which equaled minus J1 divided by omega C. And the same thing happened over here, and this is an ohm value. And XC was the same, minus J1 divided by omega times C. This was also an ohm value. XL was J omega L in both domains. Notice again that these are ohm values. J omega L in ohms. And then the resistors were real numbers, and their value were, our unit, if you want to say, was in ohms. Okay, so we have everything's the same except when we go to RMS, I'm just going to say it's already an RMS value and it's already been divided by the square root of 2. Okay, so let's just cover that stuff one more time about leading and lagging and impedance, because I'm fixing to go straight into ELI the ICEman and why we use it. And no, I can't write very straight, I'm sorry. This is the real axis. This is the J, or imaginary axis. This is the positive J axis. This is the negative J axis. And capacitors, this is an XC value. There we are. XC value. We have an XL value. And then out on the real axis, we have a resistor value. Okay, we have a resistor value. Anything between the positive J axis, and the real axis, you have an impedance Z equals R plus JXL. Okay, this is a lagging, the current lags the voltage. So basically what that means is the current angle, the angle of the current, will be smaller than the angle of the voltage. A lagging network. The current angle is smaller, less than the angle of the voltage. All right. Anywhere between the real axis and the minus imaginary axis, Z equals R minus JXC. And this is a leading network. And what this means is the angle of I is greater than the angle of V. And it can be anywhere from, small, 1 degree, to all the way up to 89 degrees. So let's talk a minute about ELI the ICEman. And this is going to be the first thing in stuff on test 3, and it will be the first part of the stuff question on final also, and it's basically, what does ELI the ICEman mean and why do we use it? So here we go. ELI the ICEman. Okay, so ELI the ICEman. Basically, ELI the ICEman says the voltage, the angle of the voltage, is greater than the angle of the current in an inductor by 90 degrees. Okay, so ELI implies that the angle of the voltage leads the angle of the current by 90 degrees in an inductor. Okay, but as power engineers, the thing is that we always talk about the current. That's what we don't know. We always know the voltage is plus or minus 5% of whatever that rated voltage is unless something happens. So we're always talking about the angle of the current and what's going on with the current. So if you're a power engineer, you're going to say that the angle of I lags the angle of V by 90 degrees in an inductor. And basically that word lags deals with the power factor. And we're not going to get into that quite yet, but next week we will. Power factor, very important in power systems. In fact, if you don't have a certain power factor and you're a customer of El Paso Electric, they will charge you extra for this. Okay, so I'm running on 14 minutes. That'll do it for this video because it takes a heck of a long time to download these things. So I'm going to stop here and I'll pick up with ELI the ICEman on the next video.